So I'm very pleased to welcome Gary Downey, a colleague I've known for a long time from Virginia Tech. He is Alumni Distinguished Professor of Science and Technology Studies at Virginia Tech and an affiliate faculty member in their Engineering Education Department. His background is very interesting, very similar to a few colleagues that I have. He started life in engineering. He has a BS in mechanical engineering from Lehigh University. He has some work experience as a co-op student when he was doing his studies, but he discovered an interest in understanding why and how people find their way to become engineers and the practice of engineering. And so he quickly branched out into cultural anthropology and got his PhD in that at the University of Chicago. From there, he went to a number of places, but he went eventually to Michigan Tech. Yeah. Is that correct, Gary? Michigan Tech to start a Science and Technology Studies program at the undergraduate level, and then Virginia Tech lured him away to start a similar program at the graduate level. And Gary is doing what is truly groundbreaking work in understanding how engineering is practiced in different countries around the world, trying to help all of us as engineers understand the differences that occur when we work with others from different countries. And I think that it's becoming more important all the time in our global an increasingly global profession of engineering to understand these issues. So I was very pleased when Gary accepted the offer to come and make this presentation, and he has strong connections to some other folks here. We have a few other folks from Virginia Tech in the department, and they were really happy to get him back. So Gary, we're very pleased to have you and look forward to the presentation.
All right, thanks very much. It's a pleasure to be here. I'd like to thank Professors Tolley, Litzinger, and Ali for the invitation to come here. I'd like to thank Kelly Williams from the department for actually getting me here, and Air Products as well for the series. So I'm a graduate of Lehigh. Air Products is just down the road and based in Allentown. A lot of my student colleagues, especially those in Chemie, went to work at Air Products and might still be there. I might look them up now. I'm really interested in the formation of engineers. We're going to start here today with a quiz. 4 questions. First question. During the summer of 1940, British freighters were sinking, victims of Nazi U-boats. Doubting its survival, the UK sent a purchasing commission to US shipyards. A deal was quickly reached, but then all progress came to a stop. To the commissioners' dismay, their ship plans proved meaningless to American engineers. The entire set of drawings had to be redrafted, and hundreds of additional drawings were needed before work could begin on building the ships that would help save the war for Britain. Explain. The answer is that the drawings had no dimensions on them. Huh. Number 2. An American engineer working in the avionics group at Honeywell reported a confusing experience with a French colleague. At a 50-minute engineering group meeting to decide the type of circuit they needed for a particular avionics system, the French engineer suddenly ran to the whiteboard and began deriving equations. This happened again on other occasions, even under severe time pressure. What was happening here? The point is that the French-trained engineer could not work on a specific problem without first deriving it from a general statement of the problem. General versus the specific, we'll talk about. Many of you know about ABET, the Accreditation Board for Engineering and Technology, and in 2000 established new general criteria for graduating engineers. Not surprisingly, first on this A through K list is the ability to apply knowledge of math and science. Of course, right? We're all good at math and science. 6th is an understanding of professional responsibility and ethics, and 8th is having the broad education necessary to understand the impact of engineering solutions in global, societal, environmental, and economic contexts. Go to Japan. The Japanese Accreditation Board for Engineering Education was established in 1999. ABET's predecessor was established in the 30s. But JABI, too, established accreditation criteria, 8 instead of 11. Applying knowledge of math and science was 3rd, not 1st. 2nd was demonstrating an understanding of social responsibility. And 1st, above all, was demonstrating an ability to consider issues from a global and multilateral viewpoint. What's the deal here? The concern is that if Japanese engineers do not consider issues from a global and multilateral viewpoint, that Japan faced the prospect of falling into a state of inferiority. Superiority, inferiority, what's that all about? Fourth, well, we won't answer this one, I'll raise it. I know we've got some nuclear engineers in the room. And I did spend the early part of my career working on issues involving radioactive waste management and nuclear power. And I have some course background in nuclear energy. But I haven't been working on that for some time. How could the engineers at the French utility company Électricité de France believe that they Frenchified nuclear power when they were using pressurized water reactor designs from Westinghouse? Sorry?
The Unix thing.
I still didn't hear.
The Unix system international.
They used a Unix system? We'll talk about that after. That's not what I'm going to say, but I'll be interested to hear.
Changed the units to SI.
SI.
That's what he said.
Oh, changed units to SI. Ah, okay. Well, that might work. They certainly did that. Yeah. Yes, they did. And I have something else. Note, it is related to the question, why are all U.S. nuclear plants custom designed? Now, that's putting it a bit crudely, but custom designed, custom built, they're very different, much different than one another than our French nuclear plants. Arthur may have something to say about that. I was just wondering, are you folks feeling pressure? The faculty now, are you feeling pressure to produce mobile engineers for a globalizing world? Are you feeling pressure from the glittering the glittering publication of The World is Flat from Thomas Friedman, the Engineers of 2020 report, which I saw in Tom's office sitting right out front? Or perhaps you're feeling the competition from places such as Georgia Tech and RPI, which are also making commitments to global engineering education. How about you students? How hard is it to find a good engineering job these days? Are you feeling pressure to become a mobile engineer in a globalizing world? Around the world today, the scale of reforms taking place in engineering education is absolutely unprecedented. It's unbelievable just how high the scale is, and more so than any other field. As I see it, there are basically two groups of reforms taking place. One involves redesigning the technical cores of engineering fields. And so, for example, in Chemie, there's a shift to multi-scale analysis. In ME, we're working on ways to figure out how to integrate in bioinfo and nanotechnologies without giving up on mechanics and the thermal fluid sciences and design and manufacturing and so on. The other one is my topic here today, and that is about building mobile engineers for a globalized workforce. Now, if you go around the world to different countries, you get this sense that everybody's adding the same things. You can find the same words repeated over and over again. Things such as teamwork, ethics, communication skills, understanding of supply chains, participation in information and computer technologies, all adding up to a new category of skill called global competence. But if we scratch just a bit below the surface, and we're able to scratch just a bit below the surface because we have access to the Tabor 710 5-finger scratch tester, see? And we are not attempting to scratch the new Droid Incredible, which is highly resistant to scratches, as you know. Rather, what we are doing is scratching below the surfaces of countries, which is what I'm going to be doing here today, excavating a little bit from the historical emergence of engineers, just to give you a little taste of some of the work that I do. And in so doing, what we're doing is practicing work in a field that I'm helping to build called engineering studies. Here are examples of the journal and 2 book series that I edit, as well as a book that's coming out here in a couple of weeks called What is Global Engineering Education For? But wait, you may say, aren't mathematical principles the same everywhere? Well, yes, in the abstract. But problems never solve themselves. As soon as you bring problems in relationship to people, you add dimensions of work, dimensions of career, dimensions of life that inflect the meaning of problems. And as you travel around the world, you find that what it means to be an engineer, what engineers have valued as their knowledge, and what is counted as engineering work has varied dramatically from place to place and over time. So when you genuinely cross the borders of countries, whether it's physically, virtually, sometimes even metaphorically, I mean, you are encountering people, both engineers and non-engineers, who understand their work differently, who define problems differently than you do. And in my judgment, this is a core issue for engineers made salient especially by globalization. My argument here in this discussion today, as well as in a book that I've nearly finished now, is that the making of engineers historically has been first and foremost, it's many things, but it's been first and foremost about the making of countries. When countries first form, somebody gets to work building engineers, developing engineering schools to produce engineers. And when countries change direction, engineers get nervous about their knowledge, and somebody gets to work changing what counts as an engineer. It is for this reason that engineering education always seems to be in a state of flux, far more than other educational fields. And the analysis today, the argument is that well, in engineering, we have this sense that if we do our technical work properly, that work will benefit humanity as a whole. There's this sense that we work on behalf of humanity as a whole. But the relationship between the work and humanity, advancing humanity, that relationship varies dramatically as one goes around the world. In other words, what counts as progress varies significantly from place to place. And I'm going to give you just a few examples here in the minutes that I have with you. We're going to take a look at 4 countries. If you want to understand the emergence of engineering, of engineers in particular, I mean, you have to take a look at France. So let's look at a few episodes in the emergence of engineering in France. I just dropped an image. Okay, we'll go back. This image. If you go back, in France we have to go back to 1700, okay? You've got to go back 300 years. Where to be an engineer meant that one worked in the military and one was working on fortifications, both building them and trying to destroy them. As an engineer in France, you were working for a sovereign who was judged to be perfect because the sovereign was appointed by God. And your service to this sovereign was defined narrowly, very specifically. Work as a military engineer, you're working on the project of managing the boundaries of the empire. Other servants, other functionaries for the sovereign worked on other projects, such as the work of managing the gardens behind the Palace of Versailles. That was Louis XIV, by the way. Or if you're in charge of managing etiquette in the court, for example. Think specific service to a perfect sovereign. Using mathematics, which was understood to be a science of action, not just description, but of action, in which your work involved approximating perfection in nature. Louis XIV supported Descartes, who made a case that God was a great clockmaker, and there lives a perfection in nature that engineers could approximate through mathematically informed, could describe mathematically and approximate it through mathematically informed work. Note that this was not judged to be progress in the sense of advancing a collection of people as a whole. This was serving a perfect leader who sat on top of this societal pyramid. Another project developed during the 19th century alongside this military project that was doing the boundaries, a project that involved organizing the interior spaces, a project of infrastructure, in which one's job was to remove the imperfections that had developed across the territory over time. This was work done by the Corps des Ponts et Chaussées, which is the Corps of building bridges and building roads across France. Again, informed by mathematics. And it's during this period that what we understand today as engineering analysis first developed, where analysis involves decomposing a problem and then recomposing it in order to achieve gain. Engineering has always been about achieving gain, and I'll come back to this. One example of the influence of mathematics is that you found in the 18th century relatively few bridges that had humpback tops on it. To have the supporting structure below grade on bridges preserved the visual experience of linearity of the road, which was desirable in a French context because, of course, we're perfecting nature. All right, the French Revolution was very significant in terms of the transfer of authority from a sovereign to people in general. But it also produced a great continuity, which is to say engineering service was still to a central location. In this case, engineers are serving the people by means of their enrollment in a school that was located in the center, located by the National Convention during the Revolutionary period, the École Polytechnique. And in joining the École Polytechnique, one was being promoted into national service, where the work involved was about developing general models of various areas of human interaction with nature. The focus on the general. Remember the general versus the specific, including such early leaders as Pierre Laplace and others. Where the work being done was to formulate general models in each area of, as I said, human interaction with nature that could inform the specific work of implementing changes that could be theorized. And these are the names that show up in engineering science textbooks, which we never look at because there are these little pictures in the bottom right-hand corner, and there's some fun facts about them, but we don't have to know it for the test. The graduates went to work for technical corps. The goal was to work for government. And through government, working for the people, engineers then were occupied an elite status responsible for helping society, the people as a whole, advance towards a future state of perfection. Progress is about advancement towards a future state of perfection. In the mid-19th century, there was some resistance. There was an effort to displace the École Polytechnique with a school that focused on private industry, producing industrial production for the purposes of consumption. But in French terms, consumption in and of itself does not count as progress necessarily because it may not be advancing towards a future state of perfection, and the effort failed. Oops. So if you count forward, basically over the next 150 years, there's a massive multiplication of schools, engineering schools across France, each of which taking on a new area of specific implementation. Because the technical corps stayed relatively the same size, the elites stayed relatively stable, and other schools that were doing specific service couldn't grow to a size larger than these schools. So what you find in France are hundreds of schools with hundreds of students. A school with 44 or 90,000 or whatever Penn State has, however you count it, is just not possible in French terms. It's in this context that we can understand, in addition to going to the metric system, we can understand how energy development in a French context is necessarily about the enhancement of social order. So for engineers who are going off into industry, one of the a desirable place to work was in testing. Because in testing, you could collect technologies from all over the world, figure out which ones are best, and then be responsible for implementing them in a way that would enhance social order. So from a French point of view, technologies to be considered valuable don't have to be built here. So it's okay if the source of a reactor comes from a vendor outside of France. But to Frenchify it, the Électricité de France selects basically two different reactor designs, two sizes, and roughly 800 and roughly 1,300 megawatt plants, and then produces dozens of them. So they have an orderly system that, and so the nuclear energy system can be judged to be a step in the direction of increased perfection. And even the calculations of economics. I mean, you find sentences that look very similar to calculations of economic calculations in the States, but it always is about order. Having low cost meant an ability to increase order because high cost electricity would undermine it. So what about the recent period? What about competitiveness and globalization? In France, a big threat to this engineering system that values work through government is a new emphasis on private industry. Because working in industry was always, in a way, a last resort or a subordinate activity for graduates. And across Europe, in a way, Europe is being formed as the territorial site that will compete with the US and East Asia on economic grounds. But to the French, this new emphasis on industry has felt like Americanization. And in that sense, vulgarization of work that's about perfection. The biggest threat to France, to French engineers, in a way, comes from within the European Union. These ministers of education got together in 1999 and said, we're going to establish a system of comparable degrees. And in the process, they shifted authority towards the center of Europe, whatever that might be, a geographical center or say Brussels, but certainly not Paris. And my point here is that the risk that gets felt is the risk of undermining the pursuit of order in favor of innovation. Innovation wasn't in and of itself valued. What's valued is the implementation of innovation in ways that enhance order. This contrasts sharply with the experiences and emergence of engineering across Britain. 75 years after after what we were talking about earlier, with the beginning with military fortifications in France, John Smeaton established a society for civil engineers. Importantly, he was not trying to form a profession, an organized profession. Rather, he was hoping that individual engineers might be judged to be professionals. He was working with a calculus, with a logic of status as a function of relative independence, where independence means that one has increased ownership over oneself. The way to think about this is to contrast the gentleman with the manual labor. The manual labor, in a way, is possessed by the rural owner, while the rural gentleman, especially the gentleman with running the big rural landed estates, is the pinnacle of then English society, the most independent. So what counts as moving up in the class system is achieving increased independence. In between manual labor and landed gentry were professionals who were quasi-independent. They had to be engaged. They had clients, so they weren't completely independent. But it was this group that engineers were trying to trying to get others to allow them to join, and they struggled, to this day. Now note, just as before, at this point, Smeaton and others were not trying to achieve collective progress. They're just trying to move up on a relatively static, stable class system. By the time we get to the mid-19th century, engineers are pumped. Engineers are excited. Engineers seem to have a really bright future as leaders of Great Britain now, not just England, but Great Britain as a whole. This is an image from the Crystal Palace of 1851, which was an industrial exposition at which time the Brits were celebrating the products of their industrial revolution, their industrial machinery. What had happened in this intervening period is indeed the Industrial Revolution, and during which a lot of people were able to elevate themselves through practical work in manufacturing industry. And engineers in particular were able to achieve significant levels of status, significant levels of income through work in manufacturing, and by designing public works projects, including Isambard Kingdom Brunel, who's standing here in front of the anchor chains for the Great Eastern Steamship, which he designed. So by the mid-1800s, things are looking really good for engineers who are working, or who first of all trained on the job through an apprenticeship system in which they work their way up from being pupils to resident engineers to assistant engineers, hopefully one day becoming a senior engineer, but valuing the practical knowledge that they gained on the job. And through their work of engineering design, they were serving all, helping society as a whole progress by, in a way, helping everyone become, achieve some sort of relative independence. The engineers characterized themselves as designers. Working with highly trained craftsmen doing the production work, their drawings had no dimensions. They were designs. They were in charge of aesthetics. By the late 19th century, in order to take advantage of some new science-based possibilities, engineers started adding formal education to engineering training. But they get outmaneuvered. During this same period, there's another significant emergence. There's another image of progress that scales up to dominance relative to material progress. And that is the achievement of relative independence through the demonstration of character. This is a high school. One of the famous British public schools, which really means private schools. This is Rugby. We could talk a little bit about Rugby, the game, and its significance in building character. Engineers found themselves struggling to demonstrate character. There was a shift of emphasis away from manufacturing in private industry to finance, where people of character were able to do work where they wouldn't have to use their hands. Engineers, still linked to manufacturing, linked to manual labor, struggling to argue for higher status. What the engineers eventually did was insert a three-year university training prior to the apprenticeship system, so they could gain some scientific knowledge that they would then it would provide backing to the practical training they would get on the job before the apprenticeship system. But they didn't give up the apprenticeship system. So what do British engineers face today? This is Ruth, who told me a few years ago that engineers are still not valued very, very highly across the UK. She's quite a good student at the University of Manchester. She said, oh yeah, if you tell someone you're an engineer in Britain, they'll say, hey, can you come fix my boiler? They think you're a mechanic. Remember France, the most elite occupation in the country. You just crossed the English Channel, and these people are struggling to demonstrate or make the case that they're higher than manual labor. In 1980, an industrialist, Sir Monty Finniston, produced a famous report with government support saying, we need a cultural change here in Great Britain, emphasizing the engineering dimension, by which he meant manufacturing. It didn't work out. It's a complex story, but it didn't work out. So what about then the emergence of economic competitiveness and globalization from engineers' points of view? Well, on the one hand, it presents a huge opportunity, an emphasis on innovation. British engineers say, hey, we're about innovation. You know, we should be leaders. Make us important. On the other hand, there's a challenge inside of Europe. On the continent, the engineering degrees are 5-year degrees, tending to end at a master's level. On the continent, they view the 3-year bachelor's degree in the UK as not really worthy of the title engineer. So there's a tension, there's ambivalence in the UK today. Why is it the case that in the United States here, the word global, and the words globalization fall so easily off our tongues? What's the deal here? To understand this, I think it's important to go back prior to the Civil War to understand that during the antebellum period in the United States, there were about 6 or 7 different ways of becoming an engineer, none of which was dominant, and each of which imagined a different kind of country. One We had West Point, which could have produced a system like France. This could have been the École Polytechnique of the United States, run with the emphasizing government. Rensselaer was an early independent polytechnic, producing gentlemen in a technical area. Didn't grow. The Erie Canal became a major site, and canals became a major site for practically trained engineers, modeling themselves on what they saw going on in Great Britain. Prior to the Civil War, it was really kind of a mess. Not until after the Civil War. In a way, not until after the Civil War did America come to know what it was. The Civil War settled what counts as progress in this country. In the 1870s and 1880s, an image of progress as low-cost production for mass consumption scales up, gains widespread acceptance. And it's during this period that university education, this is Justin Morrow, author of the Morrow-Land-Grant Act, there's the act, and here's one of the schools that grew. We have an educational system that grows, in a way, mass producing students to fit this new system of mass production, and it literally becomes a system of mass production for consumer benefit. The idea being that increasing the material welfare of people as a whole, it counts as progress, in sharp contrast with what was understood in France. So to get a Singer sewing machine, it was an enormous deal. You know some of the story here. The great emphasis is placed upon Henry Ford and mass production, and you may know something about Ford's displacement actually by General Motors, which started to segment its market and provide vehicles for specific parts of the market. The point being that engineers came to accept that in order to help achieve human progress, we needed to elevate people's material welfare generally. And to do so through companies was a necessary and appropriate vehicle. So engineers became attached to corporations at a very early point. This was steel production. Oh, I skipped over a point here about nuclear power. So very simply, by the time we get to the 1950s, 60s, 70s, and one area of energy development is nuclear power, it makes perfect sense that the way we build nuclear power plants is for utility companies to come to vendors and say, I want a 1,425 megawatt plant because that fits my planning model for the future based upon all the work I've been doing in building these coal-fired or oil-fired plants. Or I need 1225 or 1523 or 862. The point is that we had a consumer-based design process in the United States. And hence the vendor said, sure, we will build what you want. That's what we do here. And a unique thing happened during the post-World War II period, during the so-called Cold War. A whole new kind of private industry developed that seems quite different than industry producing a low-cost production for mass consumption. But what was taking place during the Cold War is there was this belief across the country that the whole system was at risk from the intrusions of communism, of socialism, which had to be stopped as a whole. So since the challenge was to the whole, the response had to be by the whole. It was during this period that the engineering education really turns to the engineering sciences. We get the so-called defense industry takes off during this period. And it is important that it's a private industry. If it were not, then we would be performing socialism. Instead, what we have is almost government through the defense industry. And the defense industry is not only for profit, but also all these huge nonprofit consulting organizations such as RAND and SRI developed during this period. In engineering, a great deal of emphasis is placed upon this guy Grinter and the Grinter Report of 1955, which made a case for emphasizing the engineering sciences in engineering curricula, which is the case. But the key stimulus to the great response, to the explosion, the rapid growth of the of the engineering sciences was that it was part of the response of, or part of the process of responding to this perceived external threat. So what's going on today as we now in the wake of the Cold War, we imagine the world as built around economic competitiveness and now the globalization of employers. From the point of view of engineers in the United States who are already expecting to work inside of private companies, to follow private companies as they move around the world is a perfectly natural process. Of course that's what we do. Why not? They're just trying to reduce costs and they're trying to help everyone. I mean, this is a contestable point, but they're trying to help everyone increase their material welfare. So why not do this? So in the US, more than really any other country, we have a tendency to extrapolate from the country and understand the country to the globe as a whole. Doesn't happen in Europe, doesn't happen in really any other part of the world because everybody else has to deal with us as well as the rest of the world. The perceived threats today no longer the military one, but they're economic. This is Beijing. Here's an image of rapidly growing India that is now the source of concern in the United States. And ABET 2000 is significantly about producing the flexible engineers who can work who can be mobile in a globalized workforce. But it's also introduced a novel ambiguity. If I work for a company whose center of gravity has moved outside the United States, am I still working for my country? And prior to globalization of industry, in really every country, engineers could assume that by working for themselves and working for their employers, they are working for their countries, and of course they're working for humanity as a whole. Now there's some ambivalence or some ambiguity about, well, gee, is it outside the U.S. or inside the U.S.? So this is an issue that globalization presents in the U.S. case in particular. One last one here fairly quickly. I'm working on this material actually right now. I'll just go through it pretty quickly here. The case of the emergence of engineering in Japan. The Meiji Restoration, the restoration of the monarchy in Japan took place in 1868. Prior to 1868, Japan was organized as, in a way, a feudal territory with one family in control as the shogun. Prior to Japan becoming a country, the leaders were from the samurai class, the leaders who understood themselves as warriors, even though they weren't allowed to fight because of the shogun. And so the fighting, in a way, took place through administrative measures, but nonetheless with a metric of warfare, where a metric of warfare being about superiority and inferiority. The concern being among samurai being about the avoidance of inferiority. This is a concern that gets built into in a way, the fabric of the country, becomes an element of the dominant image of progress across Japan with its establishment. As I was saying before, when a country gets established, somebody gets to work building engineers. What the Japanese did was invite a bunch of Brits in to establish the Imperial College of Engineering. The Brits trained engineers and as soon as they were the Japanese engineers knew enough to be able to teach, they sent all the Brits home, and the school became Japanese. And that process, which is repeated over and over again, is, in a way, a Japanese process. From an American point of view, it's often called copying. But from a Japanese point of view, it's not copying. It is making it Japanese. Once we can produce it ourselves, it becomes Japanese. And if you measure yourself constantly in a metric of superiority and inferiority, the great concern was that the West was superior. You go and learn what you can from those who are superior, and then you incorporate it in and become strong yourself. There's more of course, there's lots more to this. I'm simplifying greatly. But they produced a Japan that was understood, and they extrapolated the concept of the family. The family in Japan is both the people and the property. So it's a concept of a household. Japan became a big household that is competing in the world with other households and at risk of becoming or remaining inferior, because when Admiral Perry from the US showed up with warships and said, could we please trade with you, that was evidence that they were inferior. So the issue is how to avoid inferiority. I'm jumping over lots of stuff, but let me just give you just one quick tidbit here about World War II. What was imperialism about for the Japanese? I mean, the concern, the fear was of American and British influence, especially across the Asia-Pacific region. And so the goal of the Japanese was to build a colonial empire that could compete, at least achieve parity with the British and the Americans, which they called the Asia-Pacific co-prosperity sphere. And it's well known, especially by Koreans and Taiwanese, that the Japanese treated Taiwan very well and brutally colonized and in fact tried to destroy Korean culture by trying to transform it into Japan. The Asia-Pacific co-prosperity sphere was geographically built around Taiwan. So Taiwan was going to be the center of the new Japanese empire. During this period, you get a massive expansion of engineering education in the private sector, producing engineers to work in industry, but the industries, they're working together to help Japan avoid inferiority. In this case, it meant supporting the military. So what's the deal now? I was in Tokyo just a couple of weeks ago interviewing engineering educators, and the head of JABI told me that what we need to do today is to be able to collaborate. We need to collaborate. Now, he didn't use the word inferiority, but he used language of inferiority. We need to collaborate around the world today because Japanese companies can't do it all by themselves. But collaboration is tricky business. We need to establish joint ventures. If we don't establish joint ventures, we are at risk of falling into a state of inferiority. So we need our engineers to be able to globalize. We need them to be able to function effectively in international contexts in order to make sure that Japan maintains a position of strength. So the concern is about falling below, not falling behind, falling below. Okay. So to what does this add up? What am I trying to do here in helping map different approaches to progress in 4 different countries? And we're working on China and Japan and India. Everybody wants to know about China and India. Some other folks are working on China. I will be working on India pretty soon. One finding from all of this that I consider really important is that engineers are designed to serve. Engineers, the knowledge that we gain is linked to broader social projects. And because of that, the technical knowledge and the technical practices that we gain, even in our purely technical engineering science courses, are teaching values. We teach values routinely in engineering courses. What I'm talking about here are values of social progress that appear all over the place inside of engineering courses. There are other kinds of values and other areas that find their way into engineering curricula. But the point is that the technical curricula of engineering are infused with all kinds of social values. And I think it's important to make this visible. Especially to folks who see themselves as doing purely technical work, apart from other stuff they call politics, usually with a word that begins with F in front of it. Okay? So what localized visions of progress? Well, visions of progress as advancement toward a future state of perfection, led by work within government. Progress as increased material comfort via manufacturing, in competition with other images of advancement via character, Images of progress as low-cost mass consumption via private industry. Images of progress as the avoidance of inferiority through strength. Teaching the same courses in these different contexts are heard as having different meanings by both the teachers and the participants. So the point being then, globalization is not one thing. Globalization is minimally many things from engineering points of view, presenting engineers with variable challenges, such as, do we really have to value private industry? How can we demonstrate both creativity and character at the same time? Do I still work for my country? Can I help my country avoid inferiority when I'm collaborating with others? How does that work? The point being here, and the point I'm trying to make, is that grappling with globalization, which is a new kind of challenge in engineering, is that it disrupts the long assumed connection that came about with the formation of countries between working for myself, working for my family, working for my employer, working for my country, working for, of course, humanity as a whole. Those links are now have become problematic in different ways in different places. So that makes global competence then a variable phenomenon. Yes, a lot of new practices are emerging. Engineers are adding new identities, and in many cases these new identities are similar across different countries. As we do, I don't know, video conferencing, for example. Everyone has to add video conferencing to what they do. My point is that what they're adding it to other identities that don't go away, that are different, which makes the significance of the new identities different or variable. So some of the variable challenges that engineers face include, I maintain, argue, and campaign for, that involve recognizing that my practices, my engineering practices, the things that I learned and I'm carrying into my work, carry localized images of progress that I take for granted, the things we don't have to talk about because we know they're simply true. And as a result, we all tend to carry our countries with us in our work. Which means that crossing the boundaries of countries challenges us to learn to work effectively with people who define problems differently, which is why I'm an advocate for global engineering education. An extension then of this argument is that to venture beyond the borders of countries, whether this means through physical travel, whether it means through virtual travel, whether it means through metaphorical travel, which is what I do in my elective class called Engineering Cultures, carries with it opportunities. And these practices will not, in and of themselves, train engineers to reflect routinely on the many value commitments that live within engineering service. Okay, it's not sufficient by any means. But the question that I ask, I always, in order to achieve something in the future, it seems to me you always have to start in the present. My view is, will such reflection, some critical self-reflection by engineers, ever become routine if we don't venture beyond the borders of countries? Thanks very much for your time.
Gary, I'm going to handle the questions, but if you could repeat them so we get them on the tape.
Yeah.
So we're open for questions, please.
And I'm going to repeat them so that they're heard on the tape. Yeah. Art?
Just a couple of questions about...
Let's see here. We're using this one.
Thank you. So just a couple of questions about France. So do you believe that this theory that you evolved, that order sort of governs their mode of thinking, is only applied to engineering or to the other facets of French society, including like the administration?
Is this image, this argument about an enhancement of order that governs practices in France, is this just about engineering or elsewhere?
Because the INA also gives most of the French presidents and things like that.
Yeah, there's two responses to that. One has to do with the word governing. What I am analyzing here are images that become accepted and in a way scale up and challenge us. That doesn't necessarily mean that they govern us. So there's tremendous variability in every context. But the point is, if we're all challenged by certain images, think about, I don't know, think about gender images. If we're all challenged by common sets of images, then more often than not, we produce pattern behavior. So I am analyzing patterns but I am making a case that, an image of progress scaled up across this territory challenges not only engineers but others as well. That doesn't mean that everyone responds in the same way. Engineers, I'm arguing, gained jurisdiction or claimed jurisdiction over the relationship between people and territory, which linked them to the development of the country. So those who are challenged in France by an image of progress as advancement toward a future state of perfection, working in other areas of government or other areas of life, I expect may be responding differently. But I am making the case that there's reasonable evidence to argue that the image and you find, I keep seeing this in lots of different readings and lots of different areas around France, that there's always this emphasis that we're moving towards, we're advancing towards, and even French historians who write about this often don't seem to be recognizing that this advancement to towards, this characterization of advancement as towards, is very much at odds with Anglo-American understandings of advancement from. So yes, I'm making a case that it's territory-wide, but I'm not saying that it governs. I am saying that there are patterns, and that one of the in engineering, a patterned response was to produce this hierarchy of educational practices and work practices that placed highest value on general mathematical modeling and work practices involving the flow from general problem formulation to specific problem formulation. Is that a fair response?
I think so. I mean, you also make the argument that at the time of the French Revolution, when a lot of these schools were founded, which was a time of great disorder, is it your contention that that's the time that the engineers sort of took over, or?
Okay. In fact, really two schools were established. Most of the engineering schools a lot of engineering schools were founded during the previous century. They stayed in place. What was different is that the National Convention added a new school on top of all of them. It did get rid of Mézières, the École Militaire, a military school, and replaced it with a low-status military school. So, yeah, my contention is that the image of political disorder, which is an accurate image, is incomplete. And I'm drawing now on quality work by historians who have researched. There's a great book by a historian by the name of Ken Alder called Engineering the Revolution. And this part of the argument I'm drawing from his work. There's a continuity across revolutions. And I first started to think about this some years ago when I read a book by a historian in Crane, Britain, who made the case that if you look at the American Revolution, the English Revolution, the French Revolution, Russian Revolution, that great continuities of class identity, were carried out in the midst of political transformation. So in this case, what was continuous from the point of view of engineers and engineering is the authority of the center. Where before it was the top of a pyramid, it became an administrative center that stands for the people as a whole. So it's still Paris is still the place. It was the place before, it is the place after, and they're desperately trying to keep it the place now. But they're wrestling with Brussels. and so at the Bologna, several years ago, the European Association for Engineering Education did a survey of its members, asking them, so what are you doing with regard to the Bologna process, which in the simplest sense involves replacing a lot of degree structures with a bachelor's-master's system. And lower status organizations in Germany are all over this, and the elite technical universities, not so much. They hate it. The representative from France, and this is in their report, said, well, this was done by the ministers of education. The ministers of education in France, the Minister of Education in France doesn't really have any authority over the technical schools. So I'd have to say, really, there hasn't been much discussion about it in France. We don't care, was his point. Tom, you might do. Oh, I should have been on this. So I should stay with you? Okay, you're going to use this. Okay.
You spoke primarily about developed countries. What should an engineer's response be to globalization as we define it as manufacturing chasing the cheapest labor wherever it might be?
So the question is, what should an engineer's response be to the, in a way, assumption in the practices of development that involve chasing down the cheapest labor wherever that might be? The engineer's response, first response to that should be, well, that sure is an American move. That's what Americans do. That's what we've done for a long time. We take that for granted. Do we always have to do that? I mean, one of the reasons why I'm working hard, well, let me put it this way. Those of you who have, I guess all of you, most of you have gone through engineering programs or are going through engineering programs, and you had to take humanities and social sciences classes, which you valued very highly, I'm sure, right? No, the major goal in those classes was that they didn't reduce your grade point average, right? Sorry.
I guess my point is really more from the standpoint of social justice.
Yes.
We're willing to allow
Yes.
People to
Yes.
produce our goods and services for $1 a day,
Right.
50 cents a day. What should be our response? Should we hurry up that process so that there's a common wage around the world?
All right, I'll jump to my conclusion. Where I was headed was, it's something that we should argue about. It's something that should be an integral part of educational practices in every field that's involved in development work, including engineering. So my point here is that a lot of liberal arts contributors to engineering education tend to make the case, and I did this early in my career, it's a lot more complex than that. It's a lot more complex than you think. It's, it is, what's going on out there is a lot more complex. And then students leave and don't know what to take with this, or what to do with, because there's nothing to take with them. The case that I'm making right now is that engineering education, engineering practices are flooded with value commitments and value considerations. And we don't see that because of what I call normative holism. Normative holism is, if I do my technical work, I help humanity as a whole. I do my technical work, I help humanity as a whole. I don't have to worry. And my argument, number one, is that relationship is highly variable, because progress means different things. And if you accept that argument, then maybe you accept the argument that there are a lot more value relationships that live inside of engineering practices. So my goal is well, I have colleagues and friends who participate in a social, there's a Engineers for Social Justice network, who make the case, look, we need to pay attention to the ways in which development work is exploiting people. I agree. My response to that is, how do you get engineers to systematically pay attention to power relations in engineering work? Do you start by saying, you're screwing the world? In my judgment, you're unlikely to get a very positive reaction out of folks who say, no, I'm not. So my approach is to let's make the discussion of the value dimensions of our work a necessary part of our work. Then we can start to debate over whether or not, I don't know, having Hewlett-Packard build its educational capacity in South America, is that a good thing, or to what extent does it have downsides that we're not paying attention to because we believe that technical work has no political or power dimensions? Is that hopefully a clear response? I'm all about calling attention to issues of social justice. My approach to it, I've got another class coming or something.
We're going to take one more and then
Okay.
let the students go. Yeah.
Okay. But if we lead with you are producing social injustice, I'm not. My judgment, or at least my personal experience, has been I haven't gotten very good responses to that. So maybe you should start to think about questions of justice when you do your work, because you're already doing value. You're doing all sorts of value considerations or performing value considerations, value judgments in your everyday work already. So let's think about some others and put them alongside.
In the policy world, it seems like for the benefit of the United States, that the United States has to be a leader in advanced manufacturing. So yes, you have globalization, but there's clearly a counter move to say that you need to bring this advanced manufacturing to a country. To be an advanced country, you need to do this. So just maybe a comment on that.
Yeah, I don't have a response to that. I'd say I'm not capable of making that assessment on two grounds. What counts as advancement? And is a Western or American model of advancement the desirable model? I mean, it might be a bit presumptuous to make the case that this model is one that should be accepted in other locations, number one. But also, this was an issue that the Small is Beautiful movement got into, and the appropriate technology movement got into. Advocates of appropriate technology said, well, wait, we shouldn't be exporting our high energy use technologies. We should develop technologies that are appropriate for these lower levels of civilization. And people in other countries say, oh, great. You want to have your fancy stuff and give us this, this crappy stuff. So I don't have a general answer to this, or a response to this comment, except to say, among engineers specifically, engineers should always be participating in arguing political and other value issues, because we live value issues. That's an integral part of what we are. And so engineers should be playing more visible, more prominent roles in every country of the world, including debating over what should count as an advanced industrial practice.
Okay, well, with that, let's thank our speaker again. So, on behalf of the department, I wanted to present you with this certificate of
All right.
thanks for delivering our Air Products Distinguished Lecture, signed by Dr. Tolle, who wanted to be here but couldn't manage to be here. And we, of course, have to give you this to proudly display.
Oh, Nittany Lion.
So thank you very much.
I'm from Pittsburgh. Pitt Penn State, a big battle all the time. Which, I don't know, Joe Paws, how long is he going to be here? Thanks a lot for coming and for staying awake here late afternoon.
Thank you.